Yeah, good morning. It's good to see so many people actually here. Hopefully the hangover isn't too bad that you can actually understand what I'm going to be talking about. So I'm going to be talking about COM, and I'm sure if you've done any Windows research, you probably have at least heard about COM. I'm going to talk about sort of COM internals, because actually a lot of people don't really know kind of how COM works under the hood. And it's kind of important to know how it works under the hood before you can really start attacking it. Then, of course, I'm going to talk about actually attacking COM in various different ways, mainly for elevation of privilege, because elevation of privilege is my kind of thing. But trying to find attack surface from, say, sandboxes or attack surface for local privest the system, and then a bit about actually how you actually reverse engineer, certainly out of process COM objects. And then finally, I'm going to talk about some bugs and features I found, and at the end I'll have a few demos, depending on how much time I have left, will depend on how many demos I can do. Now, I've been writing a tool for about 5 or 6 years, and I recently, when I restarted my COM research, I decided it really needs some updates. And so I did a lot of updates before this conference, but you can go and download it. It's just on GitHub. If you go to my GitHub page, there is actually a releases tab as well, so there's some binary releases, so you don't actually need to compile it. So let's get straight into internals. And as I say, hopefully people have had their coffee. Because people think COM is scary, but COM is just middleware. COM basically just sits between one component and another component and bridges that gap. That's kind of all COM does. People think COM is more than that, but it's not. But COM came out of an actual need for a technology which allowed interoperability between applications. And this technology was something called Object Linking Embedding, or OLE. Now, there was an OLE version 1, and this was using a technology called Dynamic Data Exchange, or DDE, to do its data transfer. But if you've ever had to deal with DDE, it's pretty nasty. So COM was developed by Microsoft for OLE version 2, and it expanded upon it, made it easier to use, easier to reason about, or so it seems. But pretty much the primary use for object linking embedding is that sort of canonical example of, I have a Word document, I want to embed a spreadsheet, an Excel spreadsheet, inside my Word document, and Word could implement the entirety of Excel in its own program, but that's not particularly very efficient, because obviously the Excel team is already writing Excel. So OLE allows Excel to run as an outside process, but you can effectively embed the UI of Excel inside Word, and Word acts as a container and can consume arbitrary components and arbitrary objects. So COM provides this interoperability layer effectively. It bridges the gap between different programming languages, it bridges the gap between different processes, and it all sort of magically works under the hood, right? Or at least it should do. But of course, that's sort of the types of places where you start to find the edge cases on that implementations, because this is all hidden from the user, right? This is all, for all intents and purposes, like black magic sitting under the hood. But COM actually specifies a relatively simple set of rules, which as long as you follow, this interoperability falls out automatically. So the first one is defining a common application binary interface. And in this case, you have a COM object. The COM object is referred to using a pointer, which could be in the heap, it could be in the stack, who knows where this is. But the only thing COM really defines is saying that pointer must point to another block of memory, which must have a pointer size value which points to a function table, a virtual function table. So we can see like a simple C implementation underneath. The thing, you define a structure which contains a number of function pointers. Each function pointer must also have its first parameter pointing to the object which you're acting upon. You then have an object structure which has your vtable pointer, and then you can just call methods on that as long as you've got an instantiated instance. Now, it's no coincidence that this ABI is remarkably similar to Visual C++'s C++ virtual function ABI. So when you define a C++ class with virtual functions, it's pretty much the exact same ABI. You've got a pointer to a virtual function table and so on. So you're more likely to see this written in C++. You would define, say, a virtual interface, a pure virtual interface, and then you can have an object which derives from one or more interfaces. But now you've got a problem for interoperability. How do you get between these interfaces? If an object supports two interfaces, well, in C++, if everything's written in C++, you could just do a cast. Yeah, that would mostly work. But in most situations, if you have, say, a pointer to interface 1, casting it to interface 2 is invariably just going to cause a crash or some undefined behavior to occur. And it's going to be even worse if the object was implemented in Visual Basic and you have no idea how Visual Basic lays out its objects. Because all it guarantees is that object is laid out in the COM form. So COM also defines a standardized interface, which all other interfaces must derive from. And this is the IUnknown interface. And it serves two purposes. It first has a reference counting mechanism. This is because, again, say you are consuming an object written in Visual Basic, C++ can't just call delete on that object because it's probably not on the C++ heap, and you don't know how to destroy it properly. So reference counting is used as the lifetime to do deallocation of an object. But for getting rid of the casting problem, we have query interface. And query interface takes as a parameter a unique identifier, a globally unique identifier called the interface ID. And so this is instead of using names, because names wouldn't be unique, but instead all interfaces must have a unique identifier. You can see in IUnknown's unique identifier at the top. It's mostly zeros, as you would expect. And what you do is you call query interface, and because every interface supports IUnknown, you can call query interface and ask, hey, do you support interface 2? And if that object does, it will return you a pointer, and then you can just release it. So this is how you basically can query for support for different interfaces and avoid the casting problem. But that's all very well and good. That's assuming you've already got an object. How the hell do you get an object in the first place? And this is where the wonderful world of the Windows registry gets involved. So if you open regedit, you'll see a registry hive, HKey classes root. Now this isn't a real registry hive. This is actually like an amalgamation of two components, parts of local machine hive and parts of current user hive. But I'm not going to go into much more detail on that. But effectively underneath that, there's a registry key called CLSID. This is referring to the class ID, and effectively this is, again, a GUID, which refers to a registered object that you can create. Underneath there, you have the string form of the class ID you want to use, and then all the registration information is listed under that. And what that actually gives you when you create, when you sort of instantiate this information, is you get a factory. So COM uses the factory idiom. It uses the factory to, again, abstract the fact that I don't know how to even allocate an object, let alone deallocate an object. So you have a class factory, again, it's just a COM object. You can call create instance, it creates you an instance. Now, I'm sure people will be going, oh my God, do I have to parse the registry to do this? Well, of course not. Like, COM also provides an API to do a lot of the work for you. And this, of course, is where a lot of the hidden magic goes on, because you have two main functions, say co-get_class_object, which just returns a class factory, and co-create_instance, which returns an instance of an object, and it hides all the implementation details from you, how you even instantiate that. Now, there's various different types of servers, and so a server in COM parlance is basically an implementation which can contain multiple classes. So the most simplest one is the in-process server, and this is just a DLL. So the registry information contains a path to a DLL, and this DLL exposes a exported method, DLL get class object. You pass it a class ID. If it knows about that class ID, it should return you a factory object, and from the factory object, create instances. Very, very simple. Now, I'm not going to talk too much about in-process servers because actually, from a privilege escalation perspective, they're not that interesting. They're interesting for, like, if you're trying to break ActiveX, for example, but not necessarily for PrivEsc. But one of the things I really wanted to talk about is is apartments. Hello? Is COM apartments, because this is one of the things that confuse people when they first start looking at COM, and it is also quite enlightening to work out how some of the other COM servers work, the outer process COM servers work. So when you use COM, you pass a apartment type you want to use. So this could be apartment threaded or multi-threaded. And what an apartment does is it says, if you create an instance of a COM class inside this apartment, no other apartment in that process is allowed to directly talk to that object. And I'll explain what that actually means in a second. Looking at the simplest one, multi-threaded apartment, there is one multi-threaded apartment per process, and any thread can opt into this. So effectively, if you create an instance in that apartment, then any other thread can just get a pointer to that object, dereference its vtable, and call methods on it. But of course, then that requires the object to implement some sort of locking mechanism or mutual exclusion to make sure that it doesn't overwrite its own, it doesn't have the race conditions and things like that. So as a lot of COM was used for things like object computing, which is obviously, which is all UI based primarily. UI on Windows has a thread affinity. If you create a window on a particular thread, in theory you can only really call methods and modify that window on the same thread that you created it on. And if you don't do that, something horrible going wrong. Probably it just won't work, but it could also crash your application, which is probably undesirable. So instead, COM also supports the single-threaded apartment model. And what this actually does is allows you to sort of reason about thread affinity for COM objects. But in this case, there are cases where another apartment kind of does want to talk to a single-threaded apartment in an instance in a different apartment. So it must have to go through some process to do that. And it is allowed, but it's a lot more work than just passing a pointer. So in this case, we have two apartments. We have a sort of apartment X and apartment Y running in different threads. I want to talk to that instance using a client in thread Y. The thing which must happen is thread X must basically create a binary blob which basically contains all the information necessary to connect to that instance. And this is passed to thread Y, and thread Y creates something called a proxy. Now the proxy implements the interface you want to call, but it doesn't obviously actually implement the real implementation. It just implements basically a marshaller. So any parameter you pass, it can marshal and pack into a blob and send potentially to this other apartment. And that's done using window messaging. So the proxy parcels up all the information, it passes it to the sort of underlying COM layers, and it posts a message to the other thread. So the other thread is presumably a UI thread, so it's listening on a message loop, and it has a window, which is created by COM, and it will just sort of pick this up and go, right, okay, I now need to call this instance in my apartment. And so this is how thread affinity works, because we're utilizing the fact that the window messaging system is already have a thread affinity to basically invoke methods in the same thread which we created the object. When that message is received, it passes it to something called the stub. The stub basically is the reverse of the proxy. It unpacks the arguments, works out which method to call, and then actually invokes the actual method on the instance object inside that thread. And so from the instance object's perspective, it only ever sees calls from a single thread. Now, if you've ever done any sort of COM programming, COM hacking, sometimes you'll try and call a method and it will just hang and it will never return from that method call. Possibly what this is if no one is listening for messages on the original thread, then nothing picks up these messages. And so thread Y will just hang forever because it has, no one's listening to it. It's shouting into the void and no one cares. So if you ever actually have to do a lot of this and you find something blocking, then you may want to check that you're actually polling for window messages. Now, you can't see these messages directly. They are effectively hidden. They're for messages only. You don't have a UI associated with them. But you can write really, really simple piece of code which just basically dumps them all on your system. And you can see all the processes on all the apartment-threaded windows which you can access. And in theory, external processes can post messages to them as well. I wouldn't recommend that in any way, of course. Anyway, moving on. So if you think about that apartment model, and you kind of grab those apartments and kind of try and pull them apart, and if you keep pulling and you keep pulling, kind of eventually you can imagine you split your process in two. And your process splits into two processes, a server process and a client process. And this is just local out-of-process COM servers. Effectively, pretty much all the same plumbing and infrastructure is used. You still have the proxies, you still have the stubs, but the only real big difference is the window messaging is now replaced by an ALPC client in this case. So just the standard RPC channel. But the other main difference is how you go about activating an object. When you're activating an in-process object, you just call load library, job done pretty much. But in the outside process case, you need to create the process which is going to host the object for you. Now you could just do that manually. The client could just create the process, but you've got sharing problems, like if a class could be used by multiple clients, well, every time a client wants to access it, it spawns a new executable. That's probably not very efficient. So as part of the RPC subsystem is something called the DCOM activator. And the DCOM activator is the system service responsible for managing instantiation of COM objects out of process. So what happens under the hood? A client process says, I want to create this class. I know it's out of process, so it talks to something called the system activator in RPCSS. RPCSS will create a new process if it needs to. If it's already there, maybe it can already actually just utilize what's already there. And the server process registers its own system activator back with RPCSS. And this is basically, because it's exactly the same object effectively, this allows RPCSS to just funnel activation information directly to that server process. RPCSS then goes, okay, activate me this object. The server process goes, sure, I know what you're talking about. I implement that class ID. It creates an instance and marshals back some sort of information back to RPCSS, which goes back to the client process, and the client can now connect to the instance. Now, the system activator is pretty simple. It has two main functions. It has get class object and it has create instance. The reason it has the two is because it saves you a round trip. By just calling create instance, you don't have to get the class factory and get that back, and then call back out and call create instance and get that back. It's just a very, very simple optimization. But both functions take two common parameters. The activation properties in, which contains all the information necessary to activate your class, and returns activation properties out, which is all the information you need to sort of then connect back to that instance of the object. And even though they look like interfaces, they're actually sort of binary blobs. Underneath the hood, they're just basically binary structures. They have a common header, which contains a list of property blobs which are associated with this structure. And then it has actually individual structures you're interested in. So for activation properties in, the most interesting one is instantiation info data. This contains things like the class ID you want to instantiate, a set of flags, things like I want to create this object running in an app container. They're all sort of supported at this level. And you pass that to RPCSS, it passes it to the appropriate location, and hopefully you get a created object passed back to you. And how it passes it back is using activation properties out. And again, it has a set of different properties, but the main one is props out info. And this contains these marshaled COM objects. And you can see right at the bottom there, an example of a hex dump of a marshaled COM object. Now, what this actually is something called the object reference. And the object reference is this binary structure which is defined for COM, which allows you to marshal objects between processes or between apartments, etc. It's used everywhere, basically. Now, there's two main types. There's the standard objref, which is used for marshal by reference. And you've also got the custom objref, which is used for marshal by value. Effectively, custom objref, you tell it a class to instantiate it load libraries that class, instantiate an instance, and then basically passes the custom data to it and initializes its own context. But I'm going to focus mainly on standard object because they're kind of, in some ways, more interesting because they're allowing you to invoke methods on a remote server. So somehow the client needs to actually connect to that service because you can actually just serialize these objects out to disk and at the later date pull them back in. So the client doesn't even need to have been actually activating the object in the first place as long as it can get one of these object structures. So the first thing the client process does is it looks up something called the object exporter identifier. So every server is assigned by RPCSS a unique object exporter ID, and a different service in RPCSS, the object resolver, can be called by the client and says, hey, do you know where this object exporter is, please? And in this case, RPCSS goes, sure, I know. It's on this ALPC port, this local RPC port, with this name, OLE with some random digits. Now, if you've ever looked in like Process Explorer or Process Hacker at the handle table, you'll see this quite regularly, like an ALPC port with this OLE blah. And this is the RPC endpoint for COM. Now, the client can then instantiate an RPC client, but it also needs to know which object it wants to talk to. Now, this could have been done like in-band inside the actual call itself, but RPC provides a mechanism to specify an object unique identifier. And the object unique identifier is like part of the RPC call infrastructure. So what COM does is it takes this other value, this interface pointer ID, which is actually a GUID size value, it's a 128-bit value, and specifies it as this object UID. It can then make the call, and at the other side, the server has a table of IPIDs, which it's registered, which it's marshaled. It can look up the IPID from the RPC call. It can look up the IPID entry in the table, and that contains all the information you need to know to get to the instance and invoke the method, like where the stub is and where the instance object is, etc. So if it's all there, it will get invoked, and you've made your call. Now, one thing I've not really talked about is these proxies and stubs in any great detail. Now, if you were just writing an RPC client for Windows, you would have an IDL file which contains the description of your interfaces. You would have to compile that IDL file. That would spit out a C file. You'd have to compile the C file into your application. But this isn't very scalable. Like, if I want to implement a new interface, and I want someone to potentially be able to call it, that person needs my IDL and would need to compile it into their application. And so it just doesn't really scale. So COM instead actually provides proxies and stubs which are created using the same in-process server activation mechanism. So effectively you register a proxy object and you register a stub object, and when the COM infrastructure wants one of these, it can just load the library, call the appropriate methods, and get back a proxy or a stub. And instead of class factory, it has its own factory interface, but it's just, as I say, create proxy or create stub. But again, this is just a COM object. Now, the final piece of the puzzle for COM and how COM actually does interaction is something called the remote unknown interface. Now, you kind of assume that, like, okay, I need to query this object from multiple interfaces, as I showed earlier. I just call query interface on the proxy, and presumably that just forwards it to the remote server. Well, kind of-ish. What actually happens under the hood is every server implements this IREM unknown interface on an object. And as part of the activation properties out, you get back the IPID, the OXID of where this remote unknown interface is. And this has three functions. As you can see, like, if you look, it's derived from IUnknown as well. So this is also a COM object, right? So it has its own lifetimes. And what you do is you pass the IPID you want to query on. So you've already got an IPID for an object. You say, query the interface on this IPID and potentially give me back that object. And so this is all, again, mostly done under the hood, but you can potentially call it directly if you get access to this remote unknown IPID. So taking that local server paradigm, and you just keep pulling it again, you keep pulling that process, and eventually, like, your entire machine splits in two. That's just DCOM. This is your remote server activation, your remote COM servers. In this case, you've replaced the ALPC RPC channel with a TCP channel, but fundamentally, it's using all the same infrastructure, as I said. Activating remote objects is pretty easy. You can just, there's a parameter for co-create instance EX, just takes a host name, also contains some authentication info, which it will become more important later. But of course, just being able to activate remote objects probably sounds like a security incident waiting to happen. And it was. Prior to XP Service Pack 2, it was a security incident waiting to happen. So in XP Service Pack 2, Microsoft did two big changes. The first change is that there is a security descriptor check for any caller coming in before it ever gets to the COM activation system. This is the COM security restrictions. Now there's two types of COM access. There's the launch access, who's allowed to actually launch new objects, and there's the access restriction, who's allowed to, from say an objdref, talk to an existing object. Now, interestingly, in the restrictions, only administrators can launch new objects. However, which will become important later on, everyone can at least potentially access remote objects. But this is only potentially, because then there's a secondary check on the actual COM server itself. And so again, you have a launch, and in this case, these are the default launch permissions. So launch is enforced by RPCSS, because that's who's creating these new instances. Whereas access is enforced in the server itself. Now, the access permission is probably most interesting. You'll see this self-SID, and the self-SID is replaced by the user which is running that COM server. So if you're running as Alice, that self-SID is replaced by Alice. And so this allows, by default, a user to access their own COM servers, but no one else, in theory, other than administrators, can access them. And another change Microsoft made in Vista is, obviously, for Internet Explorer protected mode, the best sandbox ever created, said all exploit writers ever. These COM servers, in theory, would be accessible from low. So actually, you do an extra check for integrity levels. Unless you explicitly register the launch permission to have low integrity, a low integrity caller cannot create an instance of that out-of-process COM server. But this isn't enforced on access. So again, potentially, if that low privilege application can get access to that objdref, it potentially can still talk to that server, even if it hasn't got low integrity set. Now, setting security is done in one of two ways. It can either be done dynamically at program time. You can basically call this function co-initialize security, which takes a security descriptor. Worth pointing out, you may think like passing null as the security descriptor would use the default, and you'd be wrong. Instead, null means no security at all, no access security. There's still the restriction. So you still need to bypass the restriction policy. But this is why the restriction policy exists, because there was an awful lot of COM servers which just said, yeah, no security, it's fine. Like, everyone can talk to me. That was probably a security incident. But you can also specify something called an app ID. You can specify an access control interface, which is like a dynamic security model. But you can only modify the access permission. You can't modify launch permission. So for that, you need to specify your security in the app ID. And the app ID, again, is another GUID, which contains information. So each class ID can potentially refer to a app ID GUID. And this app ID is in the registry and contains things like launch permissions and access permissions. And this is the only way you can change access permissions. It also does other stuff. It says, for example, this COM server is actually implemented inside a service. And RPCSS will even start the service for you. Now, the final interesting thing about from a sandbox attack perspective is something called the interactive user run-as. So by default, if nothing else is specified, COM servers run in the mode called activator's activator. And what this basically means is, if I'm a sandboxed application, I want to create an instance of a server, it will create me running under my identity. However, if the app ID specifies interactive user, as long as the sandbox client has permission to create a new instance of that server, it actually gets created outside the sandbox. And so these are good targets for you if you're going to look for sandbox escapes, especially from something like Edge or Internet Explorer. Okay, so hopefully that wasn't too painful, because that was the internals part. So now it's getting to the actual more interesting stuff. Finding attack surface, reverse engineering, and actually sort of bugs and features. So when you're talking about sandbox stuff, there's usually two ways of getting access to objects. Either it could be activated via a broker. So Internet Explorer has a low integrity broker which will say, you can create these COM servers, and then it relies on access permissions to limit who can then talk to them afterwards. Also, as I say, with Interactive User, you can just create them. As long as you've got permission, you can create them. My tool actually has like a simple GUI to say, given this process, tell me all the COM servers which I could theoretically access. So you can use it against Edge content process, for example. And one of the things Microsoft have changed in Creator Update for Edge 15 is something called low privilege app containers. And they made a big song and dance on a blog post about how they've reduced COM attack surface. And they have, by half, I suppose, which is pretty good. But yeah, on Creator Update, you've got maybe 20 classes you can talk to. On Edge, on Anniversary Update and earlier, you've got about 40 you can talk to. And these are all ones which can run outside the sandbox, so potential good targets for attack. Now, when it comes to actually reverse engineering, if you're just at in-process servers, that's a piece of piss. You've just got a DLL loaded into your process, look up the vtable address, you can look that up in IDA or wherever, and reverse engineer it that way. But for out-of-process servers, obviously, that doesn't exist, because the implementation of this server is somewhere else, and you have no idea where that else is necessarily. Fortunately, COM is generous enough to provide us a little in to work out where that COM server is residing. And you can do this using the interface pointer ID, the IPID. You'd think the IPID, it's a GUID, it'd just be a random number, like just completely randomly generated. And it kind of is, in part. But COM fills in numerous other pieces of information. And probably the most important one for our purposes is the process ID. And the process ID, obviously, is the process ID of the COM server which hosts the implementation of that object. Oops. So we can, if we want to find where an out-of-process COM server is residing and try and do reverse engineering, we can create an instance of it, and if we marshal it, we can get its IPID. And the IPID contains the process ID. In this case, it's WMI, so it's residing in service host. We can then, my tool will also parse the IPID table for you if you've got symbols for COM base. Parse the IPID table, you can look up the IPID in that table. You can then look at the properties of that IPID, and that contains the pointer to the vtable of that object instance. And from there, you can then do reverse engineering for that object. vtable reverse engineering is pretty simple. Like if you've done any reverse engineering of C++ objects, you'll know this off by heart. The only thing to bear in mind is obviously the first three functions are all unknown or all part of that. So anything after that is potentially specific to the object itself. Of course, not all these functions may be accessible over a COM interface. For example, if the object also implements other virtual functions, it probably will end up in that table, but you can't call it via the COM proxy or stub. And then actually finding parameter information. Most stuff is written in C++, so if you have public symbols, there's probably mangled symbols. You can pull out basic parameter information. Some COM servers have type libraries, and type libraries are a description format for COM servers and COM interfaces. And you can obviously parse that information and look there. And also these proxies and stubs, most of them use something called network data representation, which is like a bytecode language for marshalling parameters between two locations. And so you can actually use this bytecode to decompile back into a semi-workable interface. You lose some information, you lose function names, you lose parameter names. You do get the interface name, you get the interface ID, and obviously you get all the parameters where possible. And you'll even get structure information. Again, you'll lose the names, but you'll at least get the structure information. So, assuming you've obviously found the things you're particularly trying to poke at, the interesting targets, I obviously did that, and I not only wanted to look for COM servers themselves, which you could abuse, but also like features of COM itself, right? Like if I can find a bug in COM, well, it doesn't matter what you've implemented in your application, I can potentially still exploit you. So the first thing when I was doing my research is looking at some of the other property information you can pass in activation properties. And this one sort of drew my eye, the special properties data blob. And it contains quite a few sort of interesting sounding things. The ones which caught my eye particularly were session ID. And session IDs usually refer to like a logon session. So if you're on a terminal server, two users logged into the same machine will have different session IDs. So maybe I can instantiate objects in a different session. That could be interesting. Also, this is where UAC gets involved. It uses its old name, LUA. I can't remember what the acronym actually means. But it's now referred to as UAC. So this is how you do elevated COM objects. You pass a particular flag to the RPCSS activation, and it will do all the activation for you. Now, you could write your own code to call directly to RPCSS, but it's actually quite a lot of kludging you need to do in there. It's pretty nasty. But fortunately, these two features are actually exposed through something called monikers. And monikers are basically string identifiers to allow you to sort of refer to certain COM objects, refer to certain COM features. And you've got something called the session moniker, which is what you can use to instantiate between sessions, and the elevation moniker, which is used for UAC. And in order to use these, you need to bind to them. And there's just a function coget object, which allows you to do the binding. And all you do is you pass a string. So in this case, I've got a string. It says session, colon, some number. That's the session ID you want to instantiate in. And then exclamation point, new, and then the class ID you want to instantiate. So the ultimate result of this is creating a COM object in a different session. Now, creating processes in different sessions is a privileged operation. You need to at least have sort of assigned primary token privilege. Just to change the session ID of a token, you need TCP privilege, which pretty much is local system only. So you would make the assumption that this object creation in a different session should also be a privileged operation. Of course, you'd be wrong. So say, for example, Alice is running in session 1 on a server and Bob is running in session 2. Alice can sort of talk to RPCSS and say, hey, can you activate me this COM object in session 2? And RPCSS, rather than saying, well, you're not an administrator, so no, it goes, sure, why not? I'll create you an object in session 2. Now, you can only create interactive user objects. So the ultimate result of that is that object gets created as Bob in that session. So the COM object is now running as Bob. And as long as then Alice has the ability to talk to Bob's process using its access permission, in theory, I can talk to a COM server in Bob's session. Now, the default had just self. And so self would be replaced by Bob in this case, and only Bob would be allowed to access it. But of course, there are other COM servers which aren't quite so picky, and they register their own custom security. In this case, a really good one was HX Help Pane server. And the HX Help Pane server had a custom access permission, which granted self, but also granted anyone who had the interactive users group, which basically meant anyone logged onto the system could access that COM server. So Alice can now talk to HX Help Pane server, and HX Help Pane server generously had a function on it called execute me an arbitrary process. Basically, it just passed the string to shell execute and would just run you an arbitrary process. Trivial cross-session activation attack, like if you're on a terminal server, you can attack anyone else running on that same terminal server. Really, really simple. Now, Microsoft have fixed this, sort of, ish, kind of. What they've done, they've fixed HX Help Pane server so that your execute arbitrary process in that session now no longer works. But that doesn't mean you can't find another COM server, right? Like any other COM server registered on that system you can access potentially can be also abused as long as you can find an interesting function. But the actual session activation has not been modified. The session activation still works. Now, another interesting thing about the IPID tables is those IPID tables contain all the information you need to connect to an object in a COM server. So if you have, say, an info disclosure, you have an arbitrary read, but not an arbitrary write, in a process, in a privileged process, you can read out the COM IPID tables. And with that information, as long as you're allowed to access that COM server through its access permissions, you can talk to any COM server in that process, only with a read access. And this is anything, even marshaled between apartments. It doesn't care that this object was marshaled to a different apartment on the same process. You can still talk to it. It doesn't have to be marshaled to another machine. Now, whether you could actually exploit that depends on the COM server, right? But effectively, you can abuse this and gain code execution and privilege escalation. But I couldn't not talk about DCOM at the end and actually remoting of objects, because I'm sure there's some people in the audience who've seen this lovely dialogue once upon a time. I can't remember which one it is. It's Code Red or something like that. Basically, they have DCOM was a shit show, basically. And if you did it wrong, RPCSS blew up and took down your system. And interestingly, I did find a local DOS which took down your system. I could get a null pointer dereference in RPCSS, and it would just basically, because RPCSS is a critical process, it just blue screens the machine for you. Kind of useless. But there we go. That's the quality of the code we're dealing with here, right? Now, when you're talking over DCOM, you're talking over, say, TCP. That's the sort of default protocol. And as everyone knows, TCP is unencrypted. So you would hope there would be some sort of encryption on DCOM calls to make sure that they couldn't be abused. And there is, if you configure it to use it, right? So the default authentication level, which is the RPC authentication level, which is used to determine whether to use things like encryption or integrity checking, is set to a level called connect. And all connect does is it does authentication. Everything else is in plain text. The PDUs, the RPC PDUs, are not even protected against replay attacks, let alone modification. So if you have a man in the middle box and they're using connect level authentication, you can potentially wait for the authentication to work and then fiddle the bits as it goes through. And for that reason, Wireshark, you can just bring up Wireshark. It has a dissector for DCOM. You can actually just look at the RPC channel. And it turns out that because everyone can bypass the restriction policy, so any, say, domain user in a domain environment could potentially bypass that initial restriction check, then as long as the COM server also allows you access, you can potentially access remote COM servers. You can't activate them, but as long as we can get an objdref, we may be able to talk to them. So in this case, WMI is configured so that any authenticated user on that system, on a remote system, can talk to WMI. So you can do something like this, which I stupidly refer to as meow jacking, of course. So in this particular case, let's assume we've got two client machines and a server. There's one client machine which is domain admin user running on it, who has permission to activate WMI on a remote server. And you have another client, a domain user, which doesn't have admin permissions, but somehow, through fortune, has the ability to monitor network traffic between those two machines. Now, a WMI activation request occurs, and the COM infrastructure marshals up that WMI object and packages it into an objdref. It then sends it back across the link, but we've now got a tap. And we can see, because it's all unencrypted, we can see that objdref as it goes past us. We can steal it and get it back to our domain user. Now, because our domain user bypasses all the access restrictions, we've not launched a new process, but we're just abusing one which has already been created for us. We can just connect to it, because the COM server doesn't realize that it doesn't really care that the person who activated the object is different from the person who accesses it afterwards. There's no per object security other than what someone implements themselves. And this is why actually it's not as bad as it sounds, because WMI actually implements its own security. So if you're a non-admin user trying to call a method on a WMI object, it gets as far as WMI, it will then do a secondary security check and say, sorry, you're not allowed to do that. But because access permissions are shared by everyone in the same process, then any COM object which you might be able to get hold of could potentially be an attack vector. And of course, remember, connect. If you have a man in the middle of connect, you potentially can wait for the authentication to come and then just change the class ID you want to activate, right? And just activate something completely different to what the domain admin was trying to create. So that is the end of the actual talking part. So I'm going to try and do a few demos. We've got sort of 5-10 minutes, so we'll see how many we can do. But first, I've got a really, really simple domain network setup. So I've got a 2016 server. Okay, and I've got, in this case, I've got one running as a normal user on the domain and one running as domain admin. Now, the domain user has this tap access to the network. So in theory, if I double-click him, I can now monitor all the DCOM traffic which is going between the dadmin user on one client and the server. So if I go in here, I'm just going to create the remote instance in here just because it reduces my, otherwise you've got a bit of a race condition, like if it releases the object before you get hold of it, it may go away before you do it. So I'll just create the instance here so you can see how it works. So I want to create it on dc-badges.local. It's my domain controller. Oops. That's never a good start. Obviously, I don't know how to type. Oops. Let's try DC. What? The demo gods are not with me today. And if my network is breaking, then there's a reasonable chance that nothing's going to work. Okay. So let's just try this again. Good thing I've got a little bit of extra time. We should actually see in here, yeah, so it did actually try and go out, and obviously something during the it just returned the error code from that. Okay, try it again, shall we? Why is it in airplane mode? Let me just plug in a network cable, see if it wakes itself all back up. Woohoo, okay. Bloody thing. All right. Okay. So that seems to be working slightly better. Okay, right. Now we've got a COM server, right? We've got a COM object we've created. And if we go back here, we can see, it's hopefully somewhere, stop him so it's not spamming me. I don't want to try Office, fuck off. Bloody Microsoft. Right, so in here we've got our remote create instance thing. If we dig in, there's various different objects, but we're looking for down here, okay, properties down, okay, awesome, interface pointers, oh yes, interface pointer, yeah, okay, interface, object, right, okay. So this is our objref for that remote object. And if we export these packet bytes, so marshall.bin, stick in the desktop, okay, we can hopefully go in here, and hopefully in here, for God's sake. Woohoo! Unbelievable. So, okay, we'll just load that file, marshall.bin. We can see it's a objref. If we click properties, we can actually look at what we got in there. And you can see it's talking to the DC. So if we click unmarshal, and we sort of wait for it to wake up, hey, we've got access to that COM server. And if we actually go and look at I've shut it off now, but basically, we've got access to that COM server. We can now invoke methods on it. Now, of course, you need to find some clever way of abusing WMI in this case, but it is potentially possible. So, because everyone likes RCE, of course, let's just demo a different RCE. So, I'm going to spawn up. So the scenario here is I've got a server which has been, or I've got a client machine, a workstation somewhere in your environment which has been compromised, and I've replaced something on that system that maybe when I try and talk to it using DCOM may go horribly wrong, right? So if I go back to my client, let me just make sure this is all set up first. So turn off the firewall, just so I can make sure I can talk to it, because otherwise it just goes wrong. Okay. So I should be able to talk to DC. Okay. Okay, so we can get rid of him, get rid of him. So if we bring up, say, PowerShell, just because it's an easy example. Okay, we can do, say, for example, get WMI object. And WMI uses DCOM under the hood, or at least the old DCOM version does. We can specify computer name of, say, domain controller. I'm assuming it's, yeah. So we now get our list of processes running on the domain controller. Now instead, if we talk to our other server, let me just check we can see him. Awesome, we can ping him. I want to see what processes are running on this other machine on my network, okay? So I run that. I can ping you, but I can't, right, awesome. And so what's then happened is I've now got a copy of Notepad running on my machine. I never got a process listing, and it's tried to create a file called pwn.txt. So obviously, it's super pwn. Like I could have run calc, right? But like, where's the fun in that, right? So I've then effectively you've tried to talk to me, so I've just gone, fuck you. I'm gonna screw you over. So maybe Microsoft will fix that soon, if you're lucky. But bearing in mind, I'm pretty much out of time. But obviously, I thank everyone for listening to me rattle on for close to an hour. But obviously, has any questions, wants to talk more about COM, you've not been completely dispirited by my description of COM, then obviously I'm here to answer questions. So thank you very much.
Do we still have the special prize for people who asked the first question? I think we have one left. Okay, so as boss informs me, the two top scores on the NOP, which apparently is really hard this year, for some reason, are also getting special limited edition. So I guess who's going to ask a question about COM is my first question, because COM is awesome, apparently. I mean, I have many questions about COM, but I'm going to wait till you're drunk. So that's how we roll. Okay, well, awesome. Thank you very much.
That's a good talk when no one even asks questions.
No one's like,
scared,
everyone's
right?
like, oh my God, what just happened to my brain? All right. Okay, now we have questions. Do it. Oh, you're going to need the mic.
So as I'm sitting here, I haven't seen much of the research on the COM stuff before, but as I'm watching it, my mind's going in a million different directions, and something I think it's interesting. I know Privesc obviously is one awesome use of this. Another one too is, I guess, for lateral movement. Do you see the potential for, I guess, kind of backdooring some of these for some kind of sneaky communications between systems as you move laterally through a network?
Yeah, so that you could, if you've compromised the machine, you could weaken the default security permissions of COM, because most people aren't really looking at that. They're just in the registry somewhere. So you could, if you weaken the default security of COM, then any other user on the same system or a malicious user on the system could access those objects remotely. And then there's plenty of rope to hang yourself at that point if you've compromised it.
Yeah, thank you.
Yeah.
All right, I think we had another question over here. Am I correct? Or we have a question way in the other side, completely other side of the room.
So I'm kind of ignorant when it comes to COM and the Windows internals. With PowerShell, is COM accessible from PowerShell, and can a potential attacker kind of leverage the PowerShell interface to manipulate COM objects for, I guess, different privilege escalation exploits, and then also for, I guess, backdooring, like the first speaker or first questioner asked?
Yeah, so PowerShell is based on .NET, and .NET was born from COM+. And so like .NET has COM interop as like a first-class language feature, effectively. PowerShell, you can instantiate new COM objects. There's the new object commandlet can take a COM class ID. It can even take a remote server, so you can create remote instances of objects. You're limited into what methods you can invoke, like dispatchable methods or methods it already knows about. But you can just add extra C#, like add type stuff, and just call methods a bit more in depth at that point. So yeah, you can do a lot of this just via PowerShell scripts.